convergence rate for non-smooth function. So our update rule is x star is equal to x minus eta g of x, where I said g of x is inside subdifferential, and we assume we have a bound for that, so that g of x is bounded by constant g for any x and any g of x. So if we just write xt plus 1 minus x star squared, it is equal to xt minus eta gt minus x star squared. And if we just expand this, we have xt minus x star squared minus 2 eta gt times xt minus x star plus eta gt squared. And I can just use the convex property. So because for any convex function y, we can write f of y is greater than f of x plus g of x times y minus x. So in simplifying this one, I can write xt minus x star squared minus 2 eta f of xt minus f of x star plus eta squared gt squared. And because this is bounded by eta 2 g2, so we are trying to find the possibility of forming a telescopic sum. So f of xt minus f of, I just put this on the left side, is less than equal to 1 over 2 eta xt minus minus x star squared minus xt plus 1 minus x star squared plus eta over 2 g squared. And I just sum over t and average that so that I can use the telescopic sum. So this is equivalent to writing like this, is it is less than 1 over 2 eta t times x1 minus x star, because you for telescopic sum, first term minus last term. So this is, I'm using the telescopic sum, xt minus x star squared plus eta 2 g squared. Notice that I can just omit this one because it doesn't matter for the inequality. And so finally, because it is a convex function, it has a property that the sum of the function, the average of the function is less than equal to f of the average of the points. So I can write this as well. And this is less than 1 to eta t. I define this as r squared. I can define this as a constant r squared. So I can write r squared plus eta 2 g2. So you see that eta is now we can take derivative with respect to eta to notice that this is equal to 1 over root of t. And because eta in this term, it increases the error. In this term, it decreases. So So we take derivative with respect to eta and put it to 0 to find that eta is this one in order to find the best balance for eta. And after that we have an error so we have an error. I just write that for if you want an error of epsilon, you should have a t of epsilon 2. So the number of steps should be this one. And so subgradient method produces epsilon optimum solution, and it is dimension free because no matter, if you just double the dimension of your problem in your machine learning problem, still you get 1 over square root of t, and this is the interesting point. So let's talk about if we have a more structure under our function, for example, beta smooth function f, then our update rule is like this: gradient of f of xt. Remember, our step size is 1 over beta. And recall that we can, for beta smooth functions, we can always write f of xt plus 1 is less than f of xt minus eta over 2 gradient of f of xt squared for any eta is less than or equal to 1 over beta. We have proved this in the last lecture. So I can use just f of xt, f of x star. Using the convexity form of f, I can write it as f of xt times x minus x star. And the last term, I don't change it. So same as usual, squared. And because this one is equal to f of x star, I can use it. I want to use the telescopic sum, so I sum it over t again. But before that, I just want to I want to use that this one is equivalent to, if you simplify this, you will notice that this one is completely equivalent to this one, xt minus x star minus eta f of x squared, and this is less than equal to f of x star plus 1 over 2 eta xt minus x star squared minus xt plus 1 minus x star 2. And this is a telescopic sum, and once we sum it, we can use the telescopic property as before, as I used for the previous part. So I can use f of xt minus f of x star is less than equal to 1 over t f of xt minus f of x star, which is less than equal to 1 over 2 eta 1 over 2 eta x naught minus x star squared. And this is 1 over t. Fortunately, we have a better error. Now suboptimality is case like 1 over t. So for error of epsilon, we get only 1 over epsilon steps, which is a great achievement in comparison to the previous case, which was just a general convex function. And note that the self-tuning property of the smooth function, here we have a self-tuning property because gradually it understands well but for the non-smooth case, we had some problem that always we have an extra term, so for example, here it is just dependent on R and no G. Remember that for the non-smooth case, we had the bound G was less than G, and plus it was something plus something depending on G. So for non-smooth case, we had an extra term G that is always that always exists there, and we cannot help them anymore. And so, but in the smooth case, we don't have such term, and so we have a better convergence rate. And you see, it's only I mean, the suboptimality scales like 1 over t only, instead of 1 over square root of t. And this is a great achievement. So you see that for the general functions, for convex functions, I proved the error, and the convex function, I only use the lower boundedness by a linear approximation. So it is a lower boundedness of linear approximation that matters. But for beta smooth, I use quadratic upper bound property. The definition of beta smooth, I recall that it is beta smooth if and only if beta over 2 x squared minus f of x is convex. And we found a better convergence rate, better achievement, rather than just using just convex. And for strongly convex, I leave it in an exercise for you. Strongly convex case, it is a strongly convex if f of x minus alpha over 2 x squared is convex. And I told you that it is quadratic lower bound. It is quadratic lower bound. So when we move from case 1 to case 2 to case 3, we try to get better convergence rates. And so you see that having a structure is really interesting and helps us in having better error and better and less error and better structure for convergence rate. And that's why these definitions of beta smoothness, strongly convex property, all of these definitions are useful, and the goal was just trying to find what happens to the convergence rate.